and what it means for an electrons to be in an excited state. So electrons, their natural preference is to be at the lowest energy state possible. And when an electron is at its lowest energy state possible, this is known as ground state. The electron configurations listed on our periodic table represent electrons in the ground state. But electrons aren't always in the ground state. So the atoms, when they are exposed to energy, the electrons within their structure absorb some of that energy. And they absorb so much energy that they become excited. So when an electron absorbs energy, it wants to move faster and in more complicated types of movement formations. So when electrons become excited, because they're going to move faster and they need more room, so they jump to a higher energy level. And that means that they jump away from the nucleus. And so when an electron moves away from the nucleus because it's absorbed too much energy, this is what we refer to as the excited state. Now, the excited state doesn't last forever. So it is temporary. So an electron cannot remain in the excited state. The excited electron, within a short amount of time, will actually release the extra energy. And when they start to release it and send it out of their structure, they release it only as light. And when the electron gets rid of that extra energy, it moves from the higher energy level, back to a lower energy level, or it moves closer to the nucleus. So an example, sodium in ground state, okay? It is, when you look on your periodic table, it gives you the configuration of 2-81. So here's its nucleus, 2 electrons in the first energy level, 8 electrons in the second energy level, and 1 electron in the third energy level. And for sodium, this is the only ground state. So the ground state, there is only one configuration. Now, this sodium, the substance that has the sodium in it, is put near an energy source. So the whole structure of sodium absorbs energy. Could be heat, could be electricity, okay? And then the electrons within the sodium become excited. So take a look. Here's a possible excited state. So we still have our nucleus. And so now we have a configuration that looks like this, right? Here's another possibility. And here's another possibility. So take a look. Here is the ground state. One or more of electrons has changed their location and has moved farther from the nucleus. So one of the electrons in the first energy level has absorbed enough energy and has popped up to the third. Take a look. In this next possibility, one of the electrons in the second energy level has absorbed enough energy and popped up to the third and moved farther away from the nucleus. And then we take a look here at this third possibility, okay, is that 2 of the electrons that should be in the second energy level, one absorbed enough energy to move to the third energy level, and the other one even more energy and jumped to the fourth energy level. And then what happens is that these electrons expend that extra energy, so they release that extra energy. But the cool thing is when they release that energy, they only release it as light. So this is the source of light energy as we know it. And the electrons all go back to their ground state. So they come back to their original configuration of 2-8-1. Now, here is something that's important to notice. In the ground state, the atom has 11 electrons. When you look at the atom's excited configurations, even though the configuration is a little bit different than the ground state one, all of these have the same number of electrons. So in the excited state, you still have 11 electrons. So you keep the same number of electrons. It's just electrons change location. They jump to a higher energy level. So that's what an excited state is there's just a rearrangement of the electrons. Same number of electrons, a location or two has changed. And then when it comes back to ground state, it still has the original 11 electrons. So watching electrons change their location, something that scientists use and have used for many years now is the bright line spectrum. So the bright line spectrum is a unique set of colorful bands of light that an atom's excited electrons give off when they go from the excited state to ground state. So if you take a look here, you start off with a light source. And the light source, it sends light towards what we would call like a prism. And the job of the prism is it brings in all of these light waves that are combined, mixed together. So I'm just going to put the word mixed light waves, okay? And that sample of mixed light waves puts into a prism, and what the prism does is it's a way to separate the light waves from each other. So this causes a separation of the light waves. And that it looks like an upside down Y. It's the Greek letter lambda, and lambda it is what science uses to represent wavelength. And then there's an instrument that you can look through, and what it does is it shows you the individual separated light bands. So in this example, this is supposed to be hydrogen. And this first line here, when you view through it, it's going to look like a violet or purple color. This next line that you will see a little bit closer to it is in the blue family. And then separated way down, you will see a band of red color. So you see these top to bottom vertical light bands. And in between those vertical bright bands, there's an absence of light. So it's just dark. So the importance of the bright line spectrum. Every element, molecule, compound out there has a unique set of color bands, okay? And what scientists do is they'll look at like the sun and the stars to determine the elemental makeup of the stars. So the scientists will compare known or established bright line spectrums to the observed ones that they see on the stars to make matches or identify any unknown elements. And they can actually tell the age of a star based on the bright line spectrums that they see. So let's take a look at the next page here. So example bright line spectrums. So when you take a look here, this is the element lithium, and these bands represent the colors that that is seen in a lithium's bright line spectrum. And down here, you will see the wavelengths. Every color of light has a measured wavelength in nanometers. And then you can see the element cadmium and then the element strontium. And then we are given a mixture. And what you will need to do is identify which of the elements are all three of these elements in this mixture, are none of them in this mixture. So this mixture is made up of what elements? And so what you need to do is just match the lines up. So the element is present in the mixture if all of its lines are there. So when you take a look at cadmium, you see these two lines here, and you look down here in the mixture, these are missing. So we don't have to look at any of the other cadmium bright lines because these two are missing. We know cadmium is not in that mixture. Now, when you look at strontium, we see these line up, line up, line up. And with the strontium, so far, all the lines that we see in the strontium's bright line spectrum, we see that they are lining up. So this mixture definitely has strontium present in it. Now, there are some lines here that don't match up to strontium. Could it be because those lines belong to the other element, lithium? So take a look. So here is a lithium line. That matches. Now all of lithium's lines have to be present. So that is definitely present. That one's present. And here's the last lithium. And it also matches. So this mixture is made up of lithium and strontium, no cadmium. Try the multiple choice questions below and check your answers with your teacher.